Okay, we're live on YouTube.
Yep.
And we're recording, so we can start.
Okay, thank you. Welcome back, everybody, to the last session of the day, the first session on post-quantum cryptography. We have 4 talks. The first talk is Practical Product Proofs for Lattice Commitments by Thomas Atema, Vadim Lubashevsky, and Gregor Seiler, and Gregor will give the talk. Gregor, the floor is yours.
Yes, thank you very much. So to position our work, so what this line of research is about is essentially fast linear-sized proof systems, which nevertheless have proof sizes that are competitive with the recent PCP-type systems in the case of small statements, and especially in those statements that are encountered in lattice cryptography. So to elaborate a bit on this, so with the PCP-type systems, I mean these proof systems like Ligero and Aurora, and they have sublinear proof sizes, for example, in terms of the circuit they're proving. And so currently, we don't know how to do this efficiently, so there's sublinearity with lattices, but there is a range of interesting statements where linear proof systems can actually give comparable or even smaller proof sizes. Yeah, as I said, for interesting statements. And this is what we're interested in. And then basically the lattice-based linear type systems, they also have very fast runtime, which are then 1 or 2 orders of magnitude faster than the PCP type systems. Now this paper is concerned with kind of one necessary ingredient for arbitrary or for basically general product proof system or general proof systems, and this ingredient is what we call a product proof. In a product proof, the goal is to be able to commit to secret vectors and then prove product relations between the coefficients of these vectors. So for example, like in the equation on this slide. So yeah, so this is really what our paper is about. And our main result is an improved product proof for a particular lattice-based commitment scheme, namely the BDLOP commitment scheme. And now to give some example for an application. So if one, or basically the simplest possible example where one only needs a product proof is a so-called range proof, where the goal is to commit to some integer and then prove that the integer lies in a certain range. Now, if the range has 1024 bit, then our product proof achieves a proof size of 31 kilobytes. So this is possible with several new techniques that we introduce and which are also useful for other protocols, not just product proofs. And in fact, these techniques, they already have been used in follow-up work, and I'm going to say something in a minute about that. So the first technique we introduce is that unlike previous works about zero-knowledge proofs for the BDLOP commitment scheme, we show how to work with non-invertible challenge pairs. So in previous works, there was always some technical problem that the difference of 2 challenge polynomials needed to be invertible, which effectively meant that one had to choose the polynomial ring in such a way that it didn't split into many small factors, or alternatively restrict the challenge set to very small size. Both of these basically possibilities resulted in quite large proof sizes, and now in our paper we show how to work with non-invertible challenges and basically get over this restriction and smaller proof sizes. And then as a second technique, we give a new analysis of some variant of the opening proof of the BDLOP commitment scheme, which means for our product proof that we show how to basically construct the protocol such that it is not necessary to send some mask opening of the secret vectors. So I call this F here now. This also results in smaller proof sizes. And then as a third technique, we show how to boost soundness of basic protocols with the help of ring automorphisms. And technically, this means that the verifier is able to compute mask openings of the secret vectors where the secret vectors are rotated by certain automorphisms sigma. And this then also achieves negligible soundless error without just repeating some simple protocols, and in effect in a way which is better than just repeating some simple protocol. Now I said the techniques have also been used in other protocols. So I want to very quickly say what basically the outlook of all of this is and what the techniques can lead to. So a natural example in lattice cryptography is being able to prove LWE samples, so knowledge of the secret in some LWE sample. And with our technique and additional techniques, so we're now able to do this with a proof size of less than 50 kilobytes. Technically, this means that one has to prove a ternary solution to some linear equation system with, say, 2048 variables. And then for some example outside of lattice cryptography, which is also interesting, so in a so-called integer relation proof, one wants to commit to several integers, say 3 of them, and prove that, for example, the product of the 2 first integers is the 3rd one. And we know how to do this with our techniques and some additional techniques to prove in the case where the integers have 128 bits. So we can do this now with 40 kilobytes and a runtime that is only 2.4 milliseconds. And this is an example for how fast our proof systems are. Yeah, with this, this is basically what I want to say for the introduction of our paper, and I'm open for questions.
Thank you. Let's see, are there any, I don't see any questions yet on the chat. Are there any questions that we could take?
So if anyone has technical problems in reaching the chat, you can also push the I'm raising my hand button somewhere in Zoom, or use the Zoom chat. So anything you can find technically you can use. I'm trying to keep an eye on every possible.
So one question, Gregor, about the techniques, if you could go back a couple of slides. Thank you. Yes. So if I understand correctly, you avoid the need for having to have an invertible pair of challenges, or invertible difference, a pair of challenges. This allows you to use fully splitting rings. Do the techniques also work even if the ring is not fully splitting, or do you need some other algebraic condition in order to make this non-invertible difference technique work?
Yes, so this technique also works in the case where the ring doesn't split fully. So essentially what we need technically is that we can bound the probability that a challenge pair is non-zero, or the difference of 2 challenges is non-zero in the NTT coefficients. And for this, it's actually enough that we can bound this probability for each NTT coefficient individually. So that in the end, we don't need the probability that the challenge is non-zero everywhere or invertible. So it's enough that we have the probability for basically one NTT coefficient at a time. And yeah, in this way, we can also use this in the case where it doesn't split fully. And yeah.
All right, thank you. Yeah. All right, I think we'll, if there are no other questions, then we'll move to the second talk of the session. So Edward. Very good. So the second talk is lattice-based blind signatures revisited by Edward Hauk, Eike Kiltz, Julian Loss, and Kan Nguyen. And Edward will give the talk. The floor is yours.
Thanks for the intro. Hi, everyone. Blind signature scheme is an interactive protocol between 2 parties, the signer and the user. The signer takes as input a secret key, the user a public key as well as a message M, where skpk is output by the keygen function. In this work, we restrict ourselves to 3 move interactions, where at the end of the interaction, the user learns a signature sigma on a message of its own choice, and the signer does not learn anything. Further, we define a public verify algorithm V, which will either output accept or reject. We consider 2 security notions, one more on forgeability and blindness. In the blindness security experiment, the adversary takes the role of a malicious signer. Intuitively, the adversary should be blind to which message was used in a specific interaction, as well as the produced signature. In the one more on forgeability security experiment, the adversary takes the role of a malicious user. For every interaction with the experiment, the adversary learns a signature. Intuitively, it should be hard for the adversary to come up with a one more forgery. Linear 3-move blind signature schemes are susceptible to the so-called ROS attack against the O-move security. The ROS stands for random inhomogeneities in an overdetermined solvable system of linear equations. The ROS attacker takes the role of a malicious user, and it does the following. First, it starts L parallel sessions with the signer. Then, with these L values R1 to RL, it computes the solution to a ROS problem. The first part of the solution will be a vector of challenge value C1 to CL, which it will send over the channel, thus receiving L responses S1 to SL. From these L responses S1 to SL, in conjunction with the second part of the solution to the ROS problem, the adversary computes L+1 signatures, thus breaking the O-move security. The bigger L, the easier the ROS problem, as the adversary learns more information. For small enough L, it can be shown that the ROS problem is information theoretically hard. In a work which recently appeared on ePrint by Benhamouda, Lepont, Orr, and Raikova, they show if L gets large enough, then the ROS attacker runs in polynomial time. In the lattice setting, the concrete hardness of the ROS problem is unknown. In the non-lattice setting, Ponchval and Stern deal with it as follows. In their seminal work, which appeared in Journal of Cryptology 2000, they give the first proof of the Okamoto snowblind signature scheme. Their O-move proof limits the range of L such that the ROS problem stays information theoretically hard. While virtually all lattice-based 3-move blind signature schemes reuse the proof techniques by Ponchval and Stern, most of them omit the part limiting the range of L, thus making their O-move security statement uncertain. In this work, we point out flaws in exactly these works. Specifically, Rückert, Asia Crypt 2000, Blaze by Al-Kadri, Bansahani, and Buchmann, which appeared in this year's Financial Crypto, and others. There, we show that an unsound application of the Belare-Nebenforking lemma leads to a gap in the O-move proof. Specifically, an argument on the outputs of the forked algorithm is missing. In our second contribution, we give a framework for blind signatures from lattice assumptions. We generalize the framework of HKL19 from the error-free setting to the setting of correctness errors. Our framework consists of the following 2 steps. We start with a linear hash function with noticeable in closeness error, when closeness error is a notion closely related to the one of correctness error. From that, we get a linear identification scheme with negligible correctness error. And from that, a linear blind signature scheme, also with negligible correctness error. Our instantiation uses the linear hash function of Lubashevsky and Michiancho, where the underlying assumption is that the RSIS problem is hard. The prime we use is quite large. So our signatures are 36 megabytes large, and the signing speed is probably quite slow due to the size of the prime. Further, the maximum number of signatures is polylogarithmic in the security parameter, as our O-move security bound degrades exponentially in the number of issued signatures. Only in this range, the ROS problem is information theoretically hard. So, all in all, our instantiation is not that practical. To conclude, we show how to construct a framework for lattice-based blind signatures with negligible correctness error, sound O-move and blindness proofs, yet the instantiation is improvable. So, as open problems, we see to find a more efficient instantiation, as well as analysis on the hardness of the generalized ROS problem. Thanks.
Thank you.
Thank you. So we are open for questions now, again, in any of the chats, or raise your virtual hand. I actually have one question, because you mentioned that you discovered an unsoundness in prior work. Does this mean that you find a flaw in the proof, but the scheme might be secure, or do you actually are the existing schemes actually insecure?
We do not give concrete attacks, but we only find a flaw in the OMOV proof.
Mm-hmm. But do you think it's kind of, I mean, does it feel like something which threatens the schemes actually, or does it feel like we just have no clue how to prove it?
This depends on the analysis of the generalized ROS problem. For our case, we can give a reduction that if the ROS problem is easy, then our scheme is not OMOV secure. And we think it might be easily generalizable to the other schemes or applicable to the other schemes. But we do not know how hard it is, in fact. So we do not know.
Okay. So we do not seem to have any other questions at the moment. So probably we can go to the next talk then.
Yes, let's have the next speaker bring up the slides. Thank you. All right, the next talk is LWE with side information, attacks, and concrete security estimation. It's authored by Dana Dockman-Saled, Leo Dukas, Huijing Gong, and Melissa Rossi. And Huijing will be giving the talk. Take it away.
So in short, our work is to integrate some leaked information of the LWE secret into the lattice reduction attack. This work has a theoretical part, which is to build a new framework for integrating the leaked secret information into the lattice reduction. It can have many applications in cryptanalysis. We include 3 applications as examples. So for motivations, let me see how to, okay. So for motivations, given an LWE scheme, to estimate its security, one standard way is to estimate the cost of primal lattice reduction attack under the parameter set of the scheme. The cost is represented by the block size of the BKZ algorithm, and which we call it beta. Many cost models can convert this beta into the bit security. For example, like usually 3 to 4 beta can convert to 1 bit security. At the end, we get the bit security that represents the estimated amount of work for key recovery. From the side channel aspect, the side channel measurement can give extra information. For example, attack with enough good measurement might be able to recover the key. For the previous work of side channel attack on LWE scheme, like most of them are using like ad hoc methods and need substantial amount of information leakage. So we are wondering, what if we get some set information and it's not enough for the key recovery? Can we actually use the lattice reduction attack and take this set information from the measurement into account? Hopefully we can see how much bit security get dropped from using this set information. Okay, so for our contribution, we actually propose a framework to integrate a certain type of set information, which we call it as a hint. And we implemented our framework on Sage, which is like over the Python. Our framework also be able to predict the security drop, and we are able to validate the prediction experimentally. As the application part of our work, we give the 3 examples. For the first examples, we use the measured data from the first attack of Boss et al.'s work. Note that their work has 2 attacks. The second attack is successful, and the first attack cannot recover the key under the reasonable amount of cost. So we take the first attack as a good example for our framework. So it turns out that our framework allows to heavily decrease the block size. For the second example, we extract the hint for the event when the decryption failure occurs. Our framework is able to reproduce the work of Devans et al. The third one, we actually extract the hint from the scheme specifications. For example, some schemes have secret generated from a ternary distribution with prescribed number of +1 or -1. And the block size decreased from such hint is actually very small. So now you might be curious about what type of the set information are included in our framework. So the first 3 types of hints are about the linear relation of the secret vector. That is, given a vector V, attacker may know the inner product of the secret S and V, or the inner product modular integer, or the inner product after some errors. The fourth type of hint is a bit different. It does not have the information on the secret, but some other information about the lattice. So our techniques for integrating the hints includes the specifying the lattice, intersecting or projecting on the hyperplanes, or altering the distribution of the secret vector. So this part is the heart of our work. We actually have very nice animation drawn by Melissa in our full talk to illustrate the geometric intuition. Yeah, okay, so thank you so much. I'm happy to take any question you might have.
Thank you very much. Mm-hmm. So any questions from the audience?
This is maybe a basic question, but would learning a little bit of the noise in the LWE distribution fit into this framework of hinting?
What do you mean learning a little bit noise? So you mean the error is sampled with smaller distributions?
Yeah, for example.
So in that one, we I think, let me see. I think yes, because in that case, the error, we kind of have extra information about the error, which the error have smaller standard deviation than the standard LWE assumptions, right? Yeah, so in that case, we can have the hint, for example, like the approximate hint, the S will be the error here, and the B will just be like identity matrix, and it will follow some distributions. Yeah, I think that would work.
I see, so S doesn't have to be the secret in the distribution per se.
Yeah, sorry for the confusion. This S is actually the including the secret vector and concatenated with the error vectors. So that is actually the short vector embedded from the canine embedding onto the lattice USVP problem. Yeah.
Thank you.
Mm-hmm. No problem.
Any other questions? Yeah, so there's one question in the chat from Mehdi Tivuchi. Is the attack expected to be more efficient, maybe in terms of required leakage, than purely statistical attacks that exploit the same type of relations?
Sorry, I'm not familiar with the statistical attack means. Could you elaborate on that?
So maybe if you have audio, you can also unmute yourself and respond to Hui Qing.
Let me see.
It's possible that Mehdi, when he says purely statistical attacks, may be referring to, yeah, like things like the Aurora attack, or that use linearization, as he said, using linear regressions, things like that.
I see. Actually, I'm not sure because we don't really compare with other attack, like, yeah, experimentally.
Mehdi added, Mehdi said thanks, so probably that answers the question. Yeah.
One more question. In terms of the 4 categories of hints that you're able to exploit, there are a couple of other things that, or variants of LWE, where, for example, the error is generated deterministically by rounding, or where you have some combination of maybe a binary secret and then wider so-called error terms. Do these fit in, or do you think there's any chance that these could fit into the framework that that you describe in this work, or would it require some additional techniques and insights?
So our there's a straightforward way to fit in our framework by, for example, for the LWR things, we can extract the covariance and also the mean from the distribution of the error. We can just explicitly sample all the AS and to see what is distribution of the error, and then we use our framework. But this also, because we only use the mean and the covariance, so actually these 2 things models the Gaussian distribution. So if the resulting real solution, real distribution is very far from the Gaussian distribution, maybe our framework cannot give you a very good result. But if very close to the Gaussian distribution, then I think that's very fitting to our framework.
I see. But if the error distribution is, for example, uniform over a small interval, or something like that, then the framework may not be a good fit for understanding that kind of problem? Or?
I think it depends on like how likely, so how good the Gaussian distribution can model the uniform distribution, but it could be a good direction for the future work to include in the different type of the distributions. Yeah.
All right, thank you.
No problem.
All right, I think we'll move to the 4th and last talk of the session. If Alexander could put up his slides.
Yes. See if it works. You see it?
We do see it, thank you.
Yeah.
All right, so the final talk of the session is a key recovery timing attack on post-quantum primitives using the Fujisaki-Okamoto transformation and its application on photochem. The work is by Qian Guo, Thomas Johansson, and Alexander Nilsson, and Alexander will give the talk, and the floor is yours.
Yeah, thank you. All right, so moving directly to, see if I can switch slides. Okay, now it works. So moving to our contribution directly, we have the result that the Fujisaki-Okamoto transform must be implemented in constant time. And this was not previously known because it doesn't handle secret data. So this is an implementation attack, but it's not previously known. So we can see that it is potentially affects a lot of different post-quantum crypto algorithms. And we have decided to show it on photochem because it's conservative design, and the designers have a clear statement on of using constant time implementations in the rest of the implementation. But in our paper, we rely on a common property of LWE and code-based schemes, which is on a high level, we have an encoding strategy where we first encode the plain text and then we add a randomized error vector or a matrix. This means that when we decode, we must remove this error vector or matrix, and we do this by either some lattice technique or a decoding algorithms. And basically, this is the property that the security hinges upon for these schemes. But what we are interested in is the fact that if we modify this error and also by extension modifying the ciphertext, we get two different outcomes. Either we modify by a small amount, which means that we get the same decoding as we would have otherwise, or we get a decryption failure. And failure in this case means that we decrypt to a different plaintext. Yeah, so the Fujisaki-Okamoto transform is using this property and basically transforms it from a CPA to a CCA secure cipher. And it does it by removing this property. And it do it like this. Here we have the decapsulation function, because I'm not having much time, so we'll focus on that. So basically what you do is you do the CPA secure version of the cipher, and you decrypt a plaintext, and then you hash it with your public key. So you get some values, and after that you re-encrypt the value that you decoded, and then you make a comparison. And basically, if you re-encrypted to the same ciphertext that the decapsulation function received, then you return the same shared secret as the encapsulation function. On the other hand, if you get a different ciphertext than what you received, then you make this results in a failure. And most often this is implemented by simply returning a different shared secret. But here we have the interesting part, because this comparison here is most often implemented with a memcompare function in C, or Java array equals, or similar functions. And the thing is that this is comparison of public values, which means that you would be forgiven to not implementing this in constant time. And this is what many schemes do, and we have shown that one must in fact implement this part in constant time as well. So moving on to a very brief description of the attack. The details are in the longer video and the paper, of course, but this is a highlight. So basically we have an algorithm where we take as input the plaintext and a modification we call D, and then we output whether or not this modification resulted in a decryption failure. So basically what we do a normal encryption, then we do a modification to the ciphertext that we encrypted, and then we simply send the ciphertext to the target, and then we measure, in our case, we measure the amount of time it takes to decapsulate our message. And then depending on the timing measurement, we decide whether or not this modification resulted in a decryption failure in the CPA decryption function. And so this depends on, using this information depends on the scheme you're actually trying to attack. And in our longer video, we are showing how we can do that on ProtoChem. But moving on to the actual measurements, we can see that if we modify our ciphertext not at all, this will be the green graph, then we get a timing profile looking kind of like this. And if we do the very minimum amount of modification to our ciphertext, we can see that nothing actually happens regarding the execution time. But if we modify the ciphertext in the maximum amount that is possible, we can see that we actually get a different execution profile. And the difference is not very big, but it is definitely measurable, as we can see here. And this brings us to some numbers. We have, like I said, tiny differences. So the measurement, the execution time is actually differs as low as 0.04%, which means we need a lots of measurements. So for one instantiation of ProtoChem, we need 97,000 encapsulations per index in the ProtoChem noise matrix, and which means that for ProtoChem 1344, we need about 2 to the 30 encapsulation queries to make a complete key recovery. And yeah, so this was very brief about our paper, and not many details, but I think or I hope you have gotten the gist of what I'm trying to show you. I guess that is it, and I can accept any question you want.
Okay, thank you very much for your talk. So we are we have several questions in the chat, and since it's the last session, I think we have the time to go through all of them. So the first question is by Tanya Lange. A question for is, would ProtoChem be saved by confirmation hashes?
I'm not quite sure what you mean by confirmation hashing. Is it because, as far as I understand it, isn't that basically what the Fujisaki-Okamoto transform is doing? You are hashing the input, because in that case, that is what we're attacking. So I'm not quite sure if I understand the question. So,
Tanya, if you can clarify the question quickly. Okay, then let me. Tanya says what they mean is include the hash of the key comma X.
okay, yes. I don't think it, I'm not sure, but the fix is very much easier than that, because you simply need to do the comparison constant time. I'm trying to read the question at the same time I'm answering, but okay. Yes, this would probably help, but like I said, I think it's easier to simply implement it in constant time. I looked at the patch from Photocam, it was very simple. So yeah.
Okay, then I will read the next question. It's by Daniel Apron. It seems like using a constant time Java equals functions calls or similar would be enough. Is that correct?
Yes.
Okay.
Yeah, I don't think I need to say any more than yes.
Okay. And then a question by Serge Ordonay. Okay, this wasn't actually a question, it was a response to Tanya. So by Serge Ordonay, it seems to me that the attack does not depend on whether the PKC is lattice-based or code-based. It only depends on the ciphertext being an array. Is that correct?
Yes, in general, but so the general part is that you can get information on decryption failure or not, even though the Fujisaki-Okamoto transform does not actually tell you. But then you need to adapt it to the cipher to actually use this information, and that's different for each scheme. But in general, yes.
By Thomas Rosa, did you consider to experiment with your side channel technique to extend the similar GPST, Galbraith Petit Shani T attack approach on Seeker, where the Fujisaki-Okamoto construction is believed to be a reliable countermeasure?
I do not recall any discussions on that. Maybe some of my co-authors remember a discussion on it. They should be here, but I suppose they can answer in the chat if they know. I do not believe we have considered it.
Okay, so we will just move to the next question, but if the co-authors have some good answer, they can just post it in the questions as a response, then Thomas will get the answer. Next question by Leo Dukas. Your conclusion is that protecting secret-related data is not enough. Can you formulate a new general principle that timing-safe implementation should aim for?
I suppose you could basically expand the definition of what is actually secret. Because the comparison basically assumes that you assume that the comparison will be always correct or equal, and anytime it is not equal, it will be an attack. And so I have not thought of this before, but I guess an expansion on what you mean by secret information would be one way. But I guess there's better. I need to think about it, but yes, probably it's possible.
Okay, thank you.
I saw a related isn't C prime secret. I just saw it in the chat, and yes or no, it's not secret to the attacker because the attacker basically constructed it.
But the attacker constructed the original ciphertext, but not the re-encryption.
Well, the re-encryption is based on the public key, and so the attacker first makes the original ciphertext, then they do a modification, so they have both.
There's a comment by Douglas Stebla who says the re-encryption is derived from secret data. After we saw this attack, he ran a taint analysis on the Photochem source code using Valgrind, and indeed it flagged the re-encrypted ciphertext as tainted by secret data. So there is a dependence of C prime on the secret data in that respect.
Yeah, because
okay,
the attacker will not know to what the ciphertext that the attacker sent decrypts, and therefore the attacker cannot predict what re-encrypting will give. I think that's why the C prime is actually secret. But I guess we should not get, we have still a few more questions, so but this is probably interesting food for thought for future discussions on this topic. Okay, so next question is by Paul Kocher. Thank you. Interesting work. Thank you. Do you think the specific comparison operation you analyzed is likely to be the only exploitable timing variation in the implementation, or are there likely to be other timing vulnerabilities as well? And if so, did you consider any more general algorithm level mitigations?
Well, the attack is specific to the comparison, but the comparison can be implemented by any non-constant time function for it to be valid. So yeah, it basically depends on whether or not the operation is constant time or not constant time. That's the only important part. Well, you can expand it to other side channel informations, like making power analysis and stuff like that, but that was not very interesting for us to do at the moment, but yeah.
Okay. I will read out three more comments that are, I think, not, they're partially questions and partially comments. So by Daniel Abram, I think this is a great paper that exemplifies a general concern. An algorithm specification is given and a security argument is given based on some computational problem. The specification is checked for general cryptanalytic attacks. For example, how do I attack the underlying computational problems? People generally become comfortable with the mathematical principle. The scheme is decent. Now further, the scheme is implemented. How do you ensure that there are no implementation problems that leak the key, etc.? I mean, this ends with a question mark, but I think it's not meant as an actual question now to the speaker, but more kind of a, well, it's also called a generic comment. And another comment by Daniel Bernstein. As a comment, TimeCop had already flagged the problem here with an automated vagrant analysis, then a link to it that I will not read out. For people who would like to check their implementations, TimeCop is integrated into the next release of SuperCop coming up in a few days. And then in addition, of course, showing that the problem is exploitable is worth a paper.
Yeah, that's good.
Okay, so that was quite an interesting discussion.
Yes.
So Chris is taking care of the time. So should we end it here or keep it going some more?
Well, I would
how
say we're comfortably over the scheduled time, and we've had a great discussion on this paper and the others. So we thank all the speakers for their talks and all the authors for their work and the audience for the great questions and discussion. And I think that will be the end of today's program, and we'll begin again tomorrow. Hope to see all of you then.
Okay. Yes. Thank